New Business Development and a co-founder of FuturePlus Systems. Barbara has over 30 years of experience in standards organizations involved in computer bus architecture. She is a member of the IEEE, is a JEDEC committee member working on DDR memory, and a VISA DisplayPort task group member. She is a frequent public speaker on topics of DDR memory and DisplayPort. Her main area of interest is in test and validation, with emphasis on finding problems prior to production. Barbara holds a Bachelor of Science in Electrical Engineering from the University of Akron and a Master's of Science in Electrical Engineering from the University of Massachusetts at Lowell. Barbara is married and has 3 children. In her spare time, she plays tennis, snow skis, and loves lake boating in New Hampshire. Please join me in giving a warm welcome to Barbara Aichinger.
Thanks, Charles. That was a great introduction. Almost makes it sound like I know what I'm talking about. Okay, so as Charles mentioned, I've been in test and measurement for quite a while. I don't like to tell how long I've been in because it kind of shows my age.
Just a couple of years.
Just a couple of years, you know what I mean? So what I'm going to talk about today is test and validation. So DDR5 validation challenges that we had over DDR4, the types of things we can do in the DDR5 system. Of course, we make test equipment, talk a little bit about that, and decision feedback equalization, which is the big challenge. And then, of course, show you some real-life systems, some traces that we have, and then talk a little bit about my favorite topic, which is row hammer and system validation, and then summarize. Okay, so some of the challenges that we face. Okay, we've had DDR5 systems in our lab for about a little over 18 months. We've had an RDIMM system, now we have a UDIMM system. SODIMMs are hard to come by as far as systems go, and then when we get them, they're very difficult to probe. So we don't have a lot of experience on DDR5 SODIMM yet. But what I'm showing you here is, the pinout here for an RDIMM. Okay, so some of the challenges. So we have 2 32-bit buses, each with ECC, on a single DIMM. Okay, on DDR4, we only had 1 bus. Okay, so what are the challenges? Well, if we're going to use a traditional logic analyzer with a passive slot interposer, okay, we could get away with maybe 1 logic analyzer card to look at the address command and control. Well, now we have 2 address command control buses, or CA buses as we call them in DDR5. So now I take 2 logic analyzer cards, so it's going to double my cost, okay, as far as the logic analyzer goes. And now I have to pay attention now. You know, I've got the B bus here, which is in the yellow and the blue. I have the A bus. I have some common signals, which are my clocks, my alert, my loopback data, and a loopback strobe. But otherwise, it's unique, okay? And now I'm going to have 2 unique clocking domains. Triggering is much more difficult. So that's one of the challenges that we face. Okay, so the next challenge that we face is on DDR5, the RDIMM, LRDIMM have a different pinout than what we have on the UDIMM. I don't know if we had a module guy talk about that earlier, Chris?
Yeah, we did yesterday.
Okay.
And tomorrow we'll have another deeper dive presentation into the
great.
modules.
Okay, so that's a challenge because on DDR4 we could have 1 slot interposer, passive slot interposer, and we could do UDIMM, RDIMM, LRDIMM, 1 slot interposer. Now, customer has to buy 2 interposers, okay? 1 for the RDIMM and the LRDIMM, and the other for the UDIMM, okay? So that's a challenge and a cost increase, okay? The SODIMM, SODIMM was difficult on DDR4. It's more difficult on DDR5, okay? The features of an SODIMM, you got the same number of bits, but from a PCB perspective, the features are incredibly small. The vias are small. The whole thing is just a lot smaller. Now we're trying to get all these probe points out. We have a solid and then flex solid. We call that a rigid flex, rigid design. And especially during COVID, when you had suppliers getting their factories shut down, it took us 3 tries to get the DDR5 SODIMM passive interposer to work. And the issues were mostly etch registration issues, okay? So it's very small. So SODIMM was hard on DDR4, it's harder on DDR5. Okay, some other challenges. Well, as you've heard everybody talk, the data signals are faster, 2x faster than DDR4. So on the DDR5 RDIMM, the CA bits are double data rate, okay? So on the UDIMM and the SODIMM, when we see them at the slot with a passive slot interposer, we see single data rate. But for the RDIMM, we see double data rate, okay?
So that's between the host and the DIMM slot.
Correct, okay? So higher speeds, lower voltages. Okay, so now the voltage on DDR5 is not that much lower than DDR4, so that's really not too big of a push-up with all the test equipment that's out there today. So the need for DFE, okay, and no I make the approaches that we used on DDR4 somewhat ineffective, okay? So now you can see here's a DDR5 RDIMM at 4,000. DDR4 CA at the top speed of 3,200. So you can see the difference in the eyes present at the slot interposer. Okay, so these are passive slot interposers. Everybody loves a slot interposer because it's easy. Just stick it in, you hook it to the logic analyzer, you stick the DIMM in there, and off you go. Okay, so as you can see, if there's no DFE in the logic analyzer, okay, it cannot grab that eye. So what does that do? That increases our bit error rate, okay, and the test equipment becomes very ineffective, okay? So some of our challenges, okay? So some more challenges. Now you had a lot of speakers today, and I'm sure yesterday, talk about the fact that we have 2 cycle commands on DDR5 versus DDR4, okay, where we had 1 cycle commands and a single data rate on DDR4. Okay, so now when I say the double data rate on the commands that's for my RDIMM and my LRDIMM, okay, so that's over here. Okay, so this is, as Chris mentioned, the double data rate CA bus is from the memory controller to the RCD on the RDIMM and the LRDIMM. So we have that nice RCD there to do some work for us, okay? And is anybody giving a talk on the RCD, Cox?
A little bit, yeah.
Okay. So the RCD is, pretty good device. We like it. And I'll show you a little bit more about why we like it. Okay, now 2 cycle commands, not that big of a push-up from DDR4 because if you've been doing LP, you've seen multi-cycle commands. Okay, so it's not that big of a push-up, but if you've just been doing DDR4, now you got to take into consideration, I got a trigger, got to set up a 2 cycle trigger to find the exact command and address I'm looking for. If you're going to be using a scope, you've got to look at some signals also. I think I have that on my next slide. Okay, so you've seen this chart before. Here's the 2 cycle commands. Again, if you're using a logic analyzer or a scope to do these triggering, well, now you've got to set up a 2-phase trigger, okay, to get the trigger that you're looking for, okay? If you're using a scope, you're going to need to look at these signals here to differentiate between a read or a write, okay? So usually when we're using a scope, we like to see a read burst, and then we like to see a write burst, okay? Well, how do you tell the difference? Okay, you've got to have, some additional signals here to differentiate between the read burst and the write burst, okay? So it's a little bit harder on DDR5, but we're managing. So decision feedback equalization. Okay, so for the RDIMM and the LRDIMM, we need it on the DQ signals. And then we also need it on the CA bits, okay, for our RDIMM. And clearly, the industry that I play into is the people that want, high reliability. They are the server vendors. They want the RDIMMs and the LRDIMMs. So that's the majority of my time is spent working with people in that industry. So in the UDIMM and the SODIMM, the DFE is only needed on the DQ signals, okay? So this is the single largest challenge that we face for the test and measurement vendors, okay? Today, the equipment does not have DFE, okay? There's no DFE in the front end of the logic analyzer, okay? There's no DFE in the front end of the scope, okay? So new hardware has to be designed to receive the signal since no I is present, okay, above certain speeds, and I'll show you a little bit about that. Now, the last time I gave this talk, which was 2.5 years ago, okay, it was anticipated that over 4,000 megatransfers per second, that the eye would close at the slot and the test equipment would need the DFE, okay? So real life, well, here we are 2.5 years later. Very close, okay? Most systems can use the passive interposer techniques with their good old-fashioned logic analyzer through the 4,000 megatransfers per second. But after that, the bit error rate of the capture increases, okay? So now you're looking at your trace on your logic analyzer and you're going, what is real and what is not real, okay? So from our experience, DFE is needed at 4,800 and above on the test equipment, okay? We'll show you a little bit more about that. Okay, so here's our real live UDIMM system, okay? And this is at some lower speeds. And you can see the read eyes, you can see the long burst there, and you can see the write eyes, and you can see the long burst there. And oh, that is just a thing of beauty, okay? In my business, you get eyes like that, and you're like, everyone's happy. Look at that signal integrity. Oh, it's wonderful. Okay, the capture that the logic analyzer would have on a system like this would be great. Okay, everyone would be happy. You'd have your job done sooner. You'd go out and play golf. Everything is great. Okay. However, as we go faster, okay, here's the DDR5 UDIMM at 4,000 megatransfers per second. So you can see we're going to have a little problem here.
I have to squint a little bit because I can't see any eyes.
Pardon?
Yeah, have to squint
yeah, your eyes, you're going to have to squint a little bit because you can't see. Okay, so you can see that the eyes are closed up here. Okay, so now those are on the DQ bits. Okay, so you can see how the writes are going to look a little bit better because where the interposer sits, okay, you got the memory controller, drives the signal. See, there's the connector, you'll see the interposer, then you'll see the DIMM under test. So we're a little bit closer to the end of the line on the writes, and so that's why the writes look a little bit better than the reads, okay? So that's some real live traces from a DDR5 UDIMM. So can the DDR5 systems be monitored like the DDR4 systems? Well, yes, at or below 4,000 megatransfers per second. The DQ signals can probably be observed in the traditional manner with your passive slot interposers and your traditional logic analyzer. The CA bits on the RDIMM and the LRDIMM are at the same speed as the DQ, so over 4,000, the eyes are going to close, as I showed you, okay? UDIMM and SODIMM have SDR on the CA, so they can be observed for a longer period of time on the traditional logic analyzer because the data rate is halved, okay, over what we see on the RDIMM CA bits. So the 2 gigahertz single data rate is easily achieved by today's logic analyzers, and if we go above 2.5 gigahertz, which is the 5,000 megatransfers per second, because we're on both edges, now you're going to start to see some problems. So how are we addressing this? Okay, so I remember when we started this, 4 years ago, we went to visit our customers who, use our equipment all the time, and we said, are you ready for life without a logic analyzer? And they said, hell no, hell no. Get busy, okay? Start doing something, okay? However, designing the decision feedback equalization into the logic analyzer was too big of a push-up, okay? Might still be too big of a push-up, I don't know, we're negotiating
Might be something
that.
that's needed eventually, right?
Pardon?
It might be needed eventually, right?
Yes, yes.
Because this will only go so far. Right?
Correct, okay? And we can talk a little bit more about that. But anyways, so test equipment needs to add the DFE. So what did we do in the short term? Okay, so we took the passive slot interposers and we put an RCD on them. Okay, and we operate the RCD in a little known feature that you will find in the spec that no one bothers to read called validation pass-through mode. Okay, so now the RCD, when you hit the RCD with chip select, he's like, hey, that's me. And he responds as if the traffic were directed at him. Okay, but if you're in validation pass-through mode, okay, which you go through the I2C bus into the RCD, and you can set up all of the registers, okay? So that's another good thing about the RCD. All of the RCD's registers are available over the I2C, I3C bus, okay? So we took the interposer, we did not use the bus, the system bus, sideband bus, or I3C. We just ran an I2C directly to that RCD, and we could put it in validation pass-through mode when the system was coming up, okay? So when you put it in validation pass-through mode, the chip select, the CA bits, the parity just pass from the input to the output, okay? So you get your cake and you eat it too. You're going to have a divide by 2 on the data rate. You're going to have a single data rate on the back side or the Q side of the RCD, and you're going to get your DFE, okay? So it's going to open up the I, okay? Now, some problems, okay? Clearly, it's not routed as I have here, okay? I can't tell you how I've routed it because that's a little bit of the secret sauce, okay? But the signals are going to have to go from the memory controller out here. They're going to hit the gold finger pins. The DQ bus is just going to pass right through. The CA bits are going to pass right through, but then those CA bits are also going to pass through here, okay? And then the RCD is in validation pass-through mode, and then you'll see these go up to the logic analyzer, okay? This is the straddle mount connector where the DIMM under test sits, okay? We also have alert and loopback data going back to the host controller, and I'll explain that in a minute. So this was our solution, okay, to the customers that said, no, we're not ready for life without a logic analyzer. Okay, so we put the RCD on there. We answer everybody's needs, and we say, however, there is a cost now. Okay, not only do you have to pay for the product, but you have to get used to what I call the new normal, okay? In the past, you could just put the passive slot interposers in there, you boot up the system, you hook up the logic analyzer, and you never had to tell the system under test that that interposer and that logic analyzer was monitoring your system. It just worked, okay? It was a wonderful thing, okay? But those days are over, okay? So now we have what I like to call the new normal. So the DDR5 memory controllers in the systems are going to have to accommodate bus monitoring tools. And it's like, ooh, they don't like that at all, okay? So why do we have to accommodate these bus monitoring tools, okay? Well, the loading is going to be increased, okay? Like I showed you in that block diagram, you know, there's a load. There's an actual RCD, an extra one, sitting on the CA bus. Not to mention the difference in the etch length on the CA as on the DQ, okay? So they got to get that all together. Thank God for DFE. Okay, so Arvin's not here today, but I was going to talk about him. So 2.5.
Feel free to talk about him.
Yeah, we're free to talk about him. I'm actually going to give him a compliment.
No, talk about him.
Okay, so 2.5, 3 years ago, when Arvin would describe DFE, he would use the word magic in the same sentence. Okay, and I'd be like, I don't believe in magic. What are you talking about here? Okay, here I am 2.5 years later. Oh, I believe in magic. Okay, because the DFE, it works. Okay, it is a thing of beauty. I really do believe in magic now. Okay, so now training for the tool will be necessary. Okay, not to the extent that you saw Howard go through today. Okay. Oh God, no, I hope we don't ever get there. We might, but we don't have to go that far, okay? So what we do is loop back data and the alert signal, other little known fun facts to know and tell about the RCD, okay? You can use both alert and loop back data by programming the RCD appropriately to take signals that are coming into the RCD and loop them back to the host, okay? So remember, a copy of those CA bits are coming into that RCD, okay? And now we want to see what they look like with respect to the signal coming back from the device under test or the DIMM under test, okay? There's only one clock, okay? It comes from the memory controller, it hits the RCD on the interposer, it hits the DIMM under test, okay? So the interposer sees it first, the DIMM under test sees it second, okay? But only one clock, okay? We don't each get our own clock. We get one clock, okay? We get a copy of that same clock, okay? So now the training, or what we like to refer to as the training, is trying to make sure that the signal coming back from the DUT and the signal being looped back from the bus monitoring tool have enough overlap, okay, so that the single clock that we're both using, we can both latch that signal, okay? So that's the new normal, okay? So training for the bus monitors, like what we kind of call training, but not as bad as, like I said, not as bad as what Howard explained, okay? So you have the chip selects on channel A, okay? They need to be trained. The chip selects on channel B, okay? The CA bits on channel A plus the parity CA bits on channel B, okay? So the object of the game is to have them, let's say the bus monitor, he feeds his guy back on alert. The RCD on the DIMM under test feeds his back on the loopback data, okay? No, we don't use loopback strobe, okay? The BIOS, okay? Everybody loves BIOS changes, right? So easy. Going to look at those two signals and determine if there's enough overlap, okay? Now, what if there's not enough overlap, okay? Then we are recommending to our customers that delays from the memory controller, okay, and the setting up of the DFE in the DUT and the bus monitor may be necessary. So remember, the bus monitor has an RCD, so he's got DFE now, okay, and all those registers are accessible, okay, to the bus monitor, okay, and so we can use delays from the memory controller and we can use DFE, okay, in the bus monitor's RCD to open up those eyes and hopefully latch the same data as being latched by the DIMM under test, okay? So now the logic analyzer, who's on the output of that RCD, follows in lockstep the commands going to the DIMM under test, which is what you want, okay, when you're doing your debug. You're trying to figure out, hey, what's going on here? What was the command that the memory controller sent out on the bus? Okay, so you want that bus monitor to see exactly what is being seen by that DIMM under test, okay? So that's the plan, okay? So what have we implemented? What's happening? What's available now in the industry? Okay, so we have your traditional passive bus monitoring. These are your slot interposers. They're passive. You know, I like to say the instrument is in the etch. They're very carefully designed. Those extremely long cables are very expensive. And we hook everything to the logic analyzer and everything works great, okay, up to a certain point, which I explained earlier. Now, how about when we put an RCD on one of these interposers, okay? So we have that right here. This is the FS2660. This is the power, okay? So we have to power that RCD because we don't want to take any bus power, right? Because really there isn't any bus power anymore, right? I'd have to put a voltage regulator on there because you got VR on DIMM now, okay? And this connector here goes to the USB of a laptop or a tower, okay? And now you can talk over that I2C goes to US, there's software that we have, you go USB to I2C and you can see all of the registers on that RDIMM, on that RCD that's on the bus interposer, okay? So now, why don't we sit on the I3C of the system? Oh, that would be great, except the system I3C bus, nowhere in the specification does it allow to have two RCDs in one slot, which is basically what we're doing, okay? Also, the current sideband bus for DDR5 allows for only one bus master, okay? So there's no way for the test equipment to get on there and, hey, I think I'm going to drive the bus today, okay? That doesn't work out. Now, that doesn't mean we might not push for that in the future, but that's one of the reasons why we just have our own connection to the RCD. So how about probing on a BGA, okay? Randy's going to talk a little bit about, tomorrow he's going to talk a little bit more about analog analysis. I'm talking a little bit more about the protocol analysis, but available we do have chip interposers, okay, that go to a logic analyzer. We also have chip interposers that go to a scope, okay? Now, what's really nice about these BGA chip interposers, okay, now obviously they're not as nice as a slot interposer because you can only go under one part, And then, of course, when you want to change the DIMMs, you've got to install that under one of those DRAMs, okay? So that can be more difficult. But you're always going to see a single data rate on the CA bits, okay? That's because if you're on an RDIMM or an LRDIMM, the DRAM CA bus sits behind the RCD. So it's on the outputs of the RCD, so you're always going to get that single data rate, okay? So that's a good thing, okay? So these are always going to be available to see the single data rate on the CA bus. So I mentioned the sideband bus. I don't know during this talk if anybody does a deep dive on the sideband, but I'm going to talk to you a little bit about the sideband. So when we started working on DDR5, started going through and all the specs, and the problem that our engineers immediately saw was that the sideband bus is just a lot more important than what we used to have on DDR4, okay? There's hundreds of registers with thousands of different settings on this sideband bus, okay? You can see here, this is an entire system would have, through this sideband bus, you would have access to all of these DIMMs, okay? So it's pretty powerful. If you're monitoring the sideband bus, you can see how everybody's set up. It's a pretty nice situation, okay? But then you're getting thousands of registers, hundreds of registers, thousands of bit settings. Okay, so now the sideband bus is, at peak it's 12.5 megahertz, it's 1 megahertz in the slow. It's only 2 signals, it's only a clock and a data. How hard could it be? Okay, well, if you like reading specs, you're going to have to read all 8 of these specs. Okay, you're going to have to start with the JEDEC module sideband bus. Okay, which refers to the MIPI I3C basic specification, so you got to get that one. Then, of course, we have the device specifications for the SPD, the serial presence detect, and the hub parts. Okay, you got to get that because you got to know all those registers. Then you got to have the contents, the SPD contents, which tells us the SPD device has non-volatile memory in there, and of course, then you got to understand what all those bits are and what all those locations mean, and so that's a different spec. It's the SPD content spec. And then, of course, you got your PMIX, right? Everybody loves the PMIX, right? That's new, VR on DIMM. You got your UDIMM and your SODIMM PMIC, and you got your RDIMM PMIC. And then, of course, you got your temperature sensors, so you got to know those, okay? And then, of course, the granddaddy of them all, and you got to understand the RCD, okay, which has, I mean, it's got so many registers and so many settings, it's mind-numbing, okay?
Oh, it's not that bad.
Oh, it's bad. Let me tell you, it's bad, okay? So now this drawing actually is in the spec, and was it last week I started sending out some emails going, do we really have 2 PMICs,
Hypothetically.
Hypothetically, that's right. So in fact, one of our colleagues, Bill Gervasi, he piped in on the email thread and said, well, Barb, you could actually have 3 PMICs. The specification allows for 3 PMICs, okay? Now, I will tell you that only 1 PMIC is on all of the approved raw cards that are out there today for DDR5.
Today.
Okay, today. There's only 1 PMIC on there, okay? You can have up to 3, and I have 2 shown here in the drawing, okay? So basically, here's the host interface. This is where we like to probe, okay, because we like to see things before they go into the hub SPD. Probing on the local side is a little bit limiting because we don't get to see all the other DIMMs in the system, and we don't get to see what's going into this SPD hub. Okay, so here, this is just another graphic pointing at all of those specifications. And then, of course, there's the module spec down here, which I didn't have in my list before that. So how do we probe the sideband bus? Okay, well, very carefully. Okay, now I know that some people have talked about using chip clips on that device right there. We chose to solder down 2 wires. Okay, we have a little flex tip adapter here. Those are just little tip resistors there, and then these are 3 stake pins which come out, okay, and then that's actually where this would attach here. I don't have a picture of our sideband bus protocol analyzer. My marketing guy is going to shoot me, but I forgot to put it on the slide. So, but that's how we probe it. I figured that was the most important thing. So let's take a look at some real life systems, okay? Like I said, we've been looking at systems for a while, so I thought I'd throw some stuff up here so you could get a feel for, what these real live DDR5 systems look like. Okay, so this is a UDIMM, just showing you here, it powers up, it goes and it reads the hub, it reads the SPD, gets the UDIMM configuration information, the density, the manufacturer, the timing parameters. One thing that we've noticed is all of the UDIMM systems that we've looked at to date only use I2C, okay? They don't switch over to I3C, okay? This is on the
Yeah, they
current.
didn't need the speed, I think.
They don't need the speed, and, but we want to see I3C, I mean, come on. But we're only looking at I2C right now on these UDIMM systems. So a little bit about the PMIC here, okay? This is just a trace of the system setting up the PMIC on the UDIMM system. So you can see there's lots of different registers and lots of different bits that get defined. You can see you're over here in the I2C mode. And it's pretty standard. One of the things that we did on a particular system was we were debugging some power issues. So one of the kind of cool things that we did was we kind of used a cross-domain triggering. We hooked up the sideband bus protocol analyzer to a logic analyzer, and then we did, they have, Keysight has a method where we can pipe the scope into the same view. And so we triggered on the enablement of the power coming out of the PMIC, and then we triggered the scope, and bam, there's the power. So it didn't look like that initially because they had a problem, and we were able to help them identify the problem, and then this is the fix. Okay, so the good thing about test and measurements is you never get blamed for the problem, but you get partial credit for the fixes. So we kind of like that. So just a little bit about the role of the hub device. So the hub has the SPD. It also has a temperature sensor. It acts as a bridge, which isolates the local bus from the host bus. It can operate in either I2C or I3C mode. And of course, as I showed earlier, it's easiest to probe this on the host side. Okay, so not that difficult. If you look at the RDIMM and UDIMM layout, you'll see that hub device is up at the top, and so it's easy to get some solder wires onto it. Okay, so now I'm going to switch gears a little bit and talk about one of my favorite topics, which is row hammer. Okay, so, and I really need to congratulate my colleagues, the two speakers that came before me. They are, DRAM vendors. They're actually, talking about this and addressing it, which is great. I'm on the test and measurement side, the validation side, so we look at it a little bit differently. Okay, and so I was very involved in row hammer when it first came out, when Project Zero broke the news 7 years ago. You had Carnegie Mellon 7.5 years ago, Yoongu Kim, how to flip bits without writing them, paper that came out of Carnegie Mellon. So, and in JEDEC, I was the first chair of the row hammer task group, but everyone assured me that it was not a problem on DDR4, which of course was not the case. So I'm happy to say that the industry is taking a much more dedicated approach. JEDEC members meet almost weekly on this topic. You heard my colleague from Micron talk about, RFM and DRFM. These are directly a result of the industry taking this more seriously. We have good DRAM supplier and industry customer participation, and personally, I've noticed a big change in customer participation in JEDEC. Ever since my colleague, and I know he's not here, Rob Sprinkle from Google, took a seat on the JEDEC board. Okay, we started to see more participation from, instead of companies that actually design SoCs or DRAMs, but the users, the very large users. Like Google must have millions and millions of DRAMs that they have in their data centers, as does Microsoft. Okay, so as does Cisco. Okay, as do some of the other vendors. Okay, so we have good participation. Okay, trying to address row hammer. Okay, a little bit about the academic papers. Okay, so they provided strong evidence. Okay, that DDR4 is vulnerable. Okay, as the vendor's targeted row refresh has been reverse engineered, okay? People mentioned that a little bit in the previous talk. So those papers come out probably 2 or 3 times a year. You can just Google them, take a look at them. They're very busy trying to break the DRAM, okay? Now, row hammer, as you heard, it's a difficult problem to solve. It impacts multiple memory technologies, not just DDR5, and it will continue to challenge the industries, okay? Suppliers, memory controller vendors, DRAM customers are all in agreement that a solution must be devised, and of course, if you talk to the people that buy these parts in the millions and millions, they will tell you that time is of the essence as security issues are increasing, okay? And the timeline for these solutions and the exact methods are being discussed. So, a little bit more, security and reliability, okay? Why is row hammer? I mean, you hear a lot about it. Without physical access to the machine, an attack that results in privileged escalation for servers has not been demonstrated yet. Okay, they talk about it, they show theoretical ways to do it, but it's not been demonstrated. A denial of service is, frankly, a lot more likely, okay? So the current and future strategy, okay, so this is a little bit of my opinion coming in here now, is buying the higher quality DIMMs, and hopefully they will be less likely to bit flips, okay? Double the refresh rate, which is what you saw come out several years ago. Everybody issued, changes to the BIOS in the server market. Hey, you got to double the refresh rate, okay? For all the reasons that the previous 2 vendors, the previous 2 speakers discussed, okay? It's a charge leakage issue. The aggressor has a lot of charge. It leaks over to the adjacent rows, and of course, we talked about the blast radius, so there could be not just adjacent, but rows several, nanometers out, okay, where that charge leakage goes and flips the bits, okay? So, doubling the refresh rate helps build up the charge of those victims, okay, so that the charge leakage is less likely to flip their bits, okay? So that's the object of the game. So what we see is making sure your workload does not inadvertently create a row hammer event, okay? Characterizing the workload for excessive activates and reads to a single row, okay? When this first started, we were just amazed to find out that Win 7, when you booted Win 7, you always wondered why that thing crashed, right? It would actually trigger a row hammer event, the booting of Win 7, okay? So this is where, you might have 2 threads going after the same location. This is how they're communicating with each other. Are you done? Are you done? Are you done? Well, I didn't set the bit yet, so this one guy's going to spin on it and he's going to read it until he sees the bit being set by the other thread. Okay, that can cause a row hammer event. Okay, and some workloads do inadvertently cause this problem. Okay, and the way you can look for that is you can use some bus monitoring tools, look at the row addresses that are constantly being gone to and see if they would exceed the threshold either specified by the manufacturer or published in the industry that we start to see row hammer events at, okay? And of course, if you're in a DDR5 system, utilize the new commands, the RFM and the DRFM commands to reduce your system's exposure to row hammer. So how will row hammer change validation? Okay, well, we're always looking at new equipment to characterize the ability of the DRAM to not flip bits when under attack. Okay, if you look at all of the academic papers, you'll see that they've all come up with all of these, attack vectors. Okay, the way that they use sideband channels and things like that to get the DRAM to flip bits. Okay, so we have to take a look at, can we somehow test that DRAM ahead of time to see how vulnerable it is to bit flips? So that's one of the things that the industry will try to tackle. Measurement tools to test that if the SoC and memory controller do the right thing when it comes to refresh management or other protocol changes that might be designed into the spec to mitigate bit flips, okay? Will the memory controller, the system, be able to recognize, hey, I'm under attack, okay, and then do the right thing using these commands to mitigate bit flips. And then, of course, as I mentioned earlier, overall system testing to see if the workloads, if your workloads, would inadvertently cause row hammer events. Okay, just to summarize a little bit. Oh, look, I'm finishing early. Aren't you lucky? Okay, DDR5 is definitely harder to validate than DDR4. Unfortunately, it's more expensive. Okay, the tools in the ecosystem are building. You'll see oscilloscopes, logic analyzers, protocol analyzers, fixtures. They're all out there. The current 4,800 mega transfers per second solutions will soon be evolving to faster. And of course, stay tuned to your favorite TNM vendor so you can make sure you have the latest information. And of course, I would hope that FuturePlus would be on that list. So is there any questions before we do our panel discussion? Or are you all just too tired and you want to hit the bar, get a drink? Go ahead, Jackson.
The additional RCD idea is pretty exciting. I like that.
Okay,
As far
great.
as the BIOS changes, at this point, does a board vendor, someone have to do those themselves, or are you getting buy-on from major CPU vendors?
Okay, so we are obviously approaching all of the CPU memory controller vendors, okay, and trying to convince them to put changes into their BIOS, okay, and we are having success at that, okay. I can't name names, okay, but we're having success. I mean, I really look at it like this: if you're a vendor, a SoC vendor, a memory controller vendor, and you want to say, hey, Mr. Customer, use my chip. Okay, I have built up the ecosystem. Okay, you can use my part with these tools. Okay, versus, well, we didn't do that. Okay, so I think the marketplace will decide and force these guys into implementing these types of things. Okay, now, oddly enough, there are some SoCs who are trying to limit their pin count so they don't have both the alert and the loopback data coming back. Okay, so they're going to have to devise some other scheme of just bringing back one signal from the RCD and one signal from the DUT. Okay, however, having said all of that, okay, what we have found is that, let's say you're in slot 0 of channel 1. Okay, once you figure out what all the settings are for the bus monitor, that's it, you're done. You only have to go through this training once. Okay, because once you figure out what the DFE setting needs to be, if there's any changes to the memory controller, you can just reload those parameters and off you go. It doesn't have to be done every time at boot time. Now, if you have a different DIMM in there, yeah, you might have to do that. So.
Thank you.
Any other questions for Barbara?
Okay, great.
Okay, thank you very much. So. Now we'll move into the panel discussion. Howard, if you'd come up, and where'd Jonathan go? He was just here. There he is. Yeah, he's hiding in the back. So we're just going to put up a couple